Hello friends, welcome to Actual Diamond Academy. In the last lecture we have started the discussion on the strings in two dimensions. So in this particular lecture we will discuss about the important terms under the common catenary. So what we have seen in the previous lecture is that a catenary is like this. Catenary is like this. Okay, so this is a string that is being tied at 2 points B and C, and these 2 points are under the same horizontal line. Okay, and the axis of this catenary is like this. Okay, and why we are using the term common catenary? Common catenary. Okay, so this catenary is the curve that is being generated by this string is a catenary, and if the weight per unit length of this catenary is constant, then we say that this catenary is a common catenary. Okay, and also we have seen that the directrix is at a distance of C from this lowest point. Okay, so this point is lowest point, that is A. So this is the basic structure of the catenary. Okay, and we have the weight per unit length of this string is small w. Okay, and this in case of common catenary, this small w is constant. Okay, weight per unit, this is capital W. Weight per unit length of the string is constant, so this is small w. Okay, so this is actually weight per unit length. So small w is weight per unit length, and capital W is weight of string. Okay, so let us consider a point P at a curved length S. Let us consider a point P at a curved length S. Okay, and now let us consider the tension at this point P is T. Okay, and tension at point A is T naught. Okay, so we have studied in the previous lecture is that this T naught is the weight of C length of the string. Suppose the length of the string is small c. Okay, so the weight of C length of the string is weight per unit length into C. This is the weight of C length of the string, and this is equal to T naught. So this we have already studied, and the T naught is the tension at the lowest point. So let us consider this point is A. The tension at the lowest point is equal to weight of C length of the string. So this we have already discussed. T naught is WC, and this value of this T is tension is equal to weight per unit length into Y. Okay, so let us consider the coordinate of this point P is x comma y. Okay, so the distance of this point P from the directrix is y. Okay, and the distance of this point P from the axis of the catenary is x. Okay, so this T is proportional to ordinate, that is distance of this point from the directrix. So this is directrix. Okay, also we have seen in the previous lecture we have the two types of equations. First one is intrinsic equation. Okay, and second one is Cartesian equation. Okay, so the intrinsic equation is S is equal to C tan psi. Okay, S is the length of the string, curved length of the string up to point P, and C is the parameter. C is the distance of the lowest point from this directrix, and psi is the angle that psi is the angle that the tension makes with the horizontal. This is psi. Okay, so the angle being made by this tension with the horizontal is this psi. Okay, and psi we can write as tan psi is equal to slope, that is dy upon dx. Okay, this psi is the inclination of the tension with the horizontal, as simple as that. Cartesian equation is y is equal to c cos hyperbolic x upon c. Okay, so this is Cartesian equation, this is intrinsic equation. So this all we have discussed in the previous lecture. Now let us proceed further with the important terms under the common catenary. So what is the axis of a catenary? So in the Cartesian equation we have y is equal to c cos h x upon c. Okay, so this is actually a even function. Okay, this is a even function of x, and the curve is symmetrical about the y-axis. So this curve is symmetrical about the y-axis. So this is y-axis. Y-axis. Okay, so since c cos h x upon c is a even function of x. So since it is a even function, so this curve will be symmetrical about the y-axis. Okay, and the vertical line of symmetry is called axis of symmetry. So this is vertical line of symmetry, and this is called axis of symmetry. Axis of symmetry. Okay, now we have vertex of the catenary, the lowest point A of a common catenary at which the tangent is horizontal. So at this particular point, the tangent is in the horizontal direction. So this point A is the lowest point, and this point is lowest point, so it is called vertex of catenary. Vertex of catenary. Okay, parameter of the catenary, the quantity C in the Cartesian equation. This quantity C in the Cartesian equation is parameter. Parameter of the catenary. And so this is called parameter of the catenary. And what is this C? So C is the distance of directrix from the lowest point. Okay, now we have the directrix of the catenary. The horizontal line at a depth C below the lowest point is known, that is axis of x. Okay, the horizontal line at a depth C below the lowest point. Okay, so this is the this directrix is at a distance of C from the lowest point. Okay, so this we have already discussed. Now we have a span and the sag. Okay, so this is the basic structure of the catenary. So this BC, this length BC is the span. Okay, and sag is this one, AD. So this distance from here, from this length to this distance is called sag. Okay, so suppose this is our catenary. Okay, and this is the horizontal one, and these are the 2 points where the strings is tied. This is B and C. So this distance, and this is the lowest point, this is A, and let us take this as D. So this AD is called sag, and this BC is span. Okay, so now let us proceed further on the important relations for the common catenary. Okay, now let us proceed further for important relations for the common catenary. Okay, so we have to find these 6 relations. Okay, so in the first one we have relation between x and s. In the second one we have relation between y and s. Third one, relation between y and psi. Fourth one, relation between x and psi. Relation between tension and ordinate. Relation, and sixth one is radius of curvature at any point of a catenary is given by rho is equal to c sec square psi. Okay, so now let us discuss this one by one. Okay, so we have a common catenary like this. This is point B, this is point C, this is the horizontal line, and this is the axis, and this is the directrix. Okay, so we have to find the relation between x and s. Okay, so we have the intrinsic equation of the common catenary as s is equal to c tan psi. Okay, and the Cartesian equation is y is equal to c cos h x upon c. So this is the Cartesian equation, and this is the intrinsic equation. So let us use this intrinsic equation. So we have s is equal to c tan psi. S is equal to c tan psi. Okay, so psi is the angle at a tension at a point P. So the tension at point P is in this particular direction. This makes with the horizontal. The angle made by this tension with the horizontal is psi, and this psi is nothing but the slope at this particular point. So tan psi is equal to dy upon dx. Okay, so s upon c is equal to tan psi, and tan psi is equal to dy upon dx. And we have the Cartesian equation as y is equal to c cos h x upon c. Let us place the value here. So s upon c is equal to d upon dx of y. So y is this c cos h x upon c. So s upon c is equal to c times of 1 upon c into sine of hyperbolic h x upon c. So this gets cancelled. So s is equal to c times of sine h x upon c. Okay. So this is the relation between x and s. So we have s is equal to c sine hyperbolic x upon c. Okay. So this we have proved. The relation between x and s is equal to c sine of hyperbolic x upon c. Now let us discuss this second one. So in the second one we have to find relation between y and s. Okay, so what we have to prove, y square is equal to c square plus s square. Okay, so we have in the terms of Cartesian equation we have y is equal to in the terms of Cartesian equation y is equal to c times of cos of h hyperbolic y is equal to c times of cos of hyperbolic x upon c, and s is equal to c times of sine of h x upon c. So this is as per this relation 1. Relation between x and s is equal to c sine of hyperbolic x upon c. Okay, so now let us find y square minus s square. So this is equal to c square, this is cos square h x upon c minus sine square h x upon c. Okay, so we have the relation as cos square hyperbolic x minus sine square hyperbolic x. This is equal to 1. So this value will be 1. Okay, let us use this. So this is y square minus s square is equal to c square. So y square is equal to s square, y square is equal to c square plus s square. Okay, so this is the proof of relation 2. Now let us discuss relation 3. Let us discuss relation 3. Let us discuss relation 3. Okay, so we have to prove that y is equal to c times of sec of psi. Okay, so we have from the relation 2 we have y square is equal to c square plus s square. So y square is equal to c square plus the value of s is, so from the intrinsic equation of the common catenary we have s is equal to c tan psi. S is equal to c tan psi. So we have this as c tan psi whole square. So y square is equal to c square plus c square tan square psi. So y square is equal to c square 1 plus tan square psi. So this is y square is equal to c square sec square psi. So y is equal to c sec psi. Okay, so this is the proof of relation 3. Now let us discuss relation 4. Relation 4 as, so we have under relation 4 we have to prove x is equal to c times of log of sec psi plus tan psi. Okay, so now let us calculate dx upon d psi. Okay, so we have dx upon d psi as dx upon ds into ds upon d psi. Okay, and we have from the intrinsic equation of the common catenary s is equal to c tan psi. So this is equal to dx upon ds into d upon d psi of the value of s is c tan psi. Okay, and let us calculate dx upon ds. Okay, so let us take this as, so the differential, this is the total curved distance is s. Okay, so the differential value of s is ds, differential value of x is dx, differential value of y is dy, and this is psi. So we have cos of psi is equal to dx upon ds, dx upon ds. So this is cos of psi into this is c times of tan of psi, differentiation of tan psi, this is sec square psi. So this is equal to c sec psi. This is dx upon d psi. Okay, so we have, let us integrate this. So dx is equal to c times of sec psi d psi. Integrate this. So this is x is equal to c times of integration of sec psi d psi is log of sec psi plus tan psi. So this is equal to c times of log of sec psi plus tan psi plus constant of integration. Okay, so let's take at x is equal to 0, at x is equal to 0, this slope is in horizontal direction. Okay, so tangent at this point is in horizontal direction, so psi is equal to 0 at x is equal to 0. So at x is equal to 0, psi is equal to 0. So when we put psi is equal to 0, this tan psi is 0 and sec of psi, sec psi, okay, so sec of 0 will be 1. So this is 0 is equal to c times of log of 1 plus a. Log of 1 is 0, so this means a is equal to 0. So we have x is equal to c times of log sec psi plus tan psi. Okay, so this is the proof of relation 3. Now let us discuss relation 5. Now let us discuss relation 5. So we have relation between tension and ordinate as T is equal to small w into y. Okay, so the tension at the lowest point is T naught, and this T naught is equal to small w into c, weight of c length of the string. This we have already discussed. So we have T naught is equal to weight of c length of the string, and we have T cos psi. T cos psi is equal to this T naught. Horizontal component of this tension is T cos psi, and T cos psi is the tension at the, this is equal to tension at the lowest point, that is T naught. This is equal to WC. Okay, T is equal to WC upon cos psi, and T is equal to WC sec psi. Okay, and we have the value of y as y is equal to c sec psi. This we have already discussed. So T is equal to W into y. Okay, so this is the tension is proportional to ordinate. Okay, so tension is proportional to the distance of this point P, distance of this point P from the directrix, that is y. So T is proportional to y. This means tension is equal to weight per unit length times of distance of this point P from the directrix. So T is equal to small w into y. Now we have to find the radius of curvature at any point of a catenary is given by this particular expression. So let us find this. Okay, so the radius of curvature is given by, radius of curvature is ds upon d psi, and the value of s is c tan psi. So this is equal to d upon d psi of s is c tan psi. So this is equal to c times of differentiation of tan psi is sec square psi. This is the value of radius of curvature. So radius of curvature is c sec square psi. Okay, so we have these two relation, that is y is equal to c sec psi, relation 3, and this is x is equal to c log sec psi plus tan psi, together constitute a parametric equation of common catenary, where psi being the parametry. Okay, so we have the relation 3 and relation 4, that is y is equal to c sec psi and x is equal to c log sec psi plus tan psi. Okay, so these two equations, these two relations together constitute the parametric equation of common catenary, where psi being parameter. Okay, psi being the parameter. Okay, so this is all about the strings in 2 dimension. So in the next lecture we will start discussing the problems. Okay, thank you.